I'm going to talk about, yes, what I'm going to call HR EBSD, but it's also known as cross-correlation-based EBSD, and really, I guess that in there should be an A missing, high resolution, a high angular resolution EBSD. So, we'll go through really from the start, what's the motivation, why did we bother to do it, and essentially we rely on going from these beautiful EBSD patterns through a Huff transform or radon transform to detect these linear features in here which become localized spotlight features in the Huff transform, which we can detect, and then we can index compare if we know something about the crystallography. And this all goes on and can go on much more rapidly than we can describe it in the current systems. I'll just re-advertise what I mentioned earlier on. There is now a MATLAB-based open source code available for you called Astro EBSD. If you go to GitHub, you can download it, have a play, contribute to it. There are bits and pieces in there that Ben and others involved in Ben Britton and his people at Imperial, myself have been involved in putting this together. We know some bits of it are not particularly good, so pick it up, make it better, put the better version on GitHub so that we can all benefit from that. You will find if you have a go with it, it's not as quick as the commercial systems, but you can tell, you can look at the detail of what's going on inside it. You've got a bit more control about what's going on. Current, you integrate for a long time, get really, really clean patterns. There's a limit in the end. We can debate exactly where that limit turns out, but a few tenths of a degree or so is your angular limit. And if you think about that, well, we move away from degrees and over to radians, that's about 10 milliradians or so. And so that's 10 milliradians, that's 10 in 1,000, okay? It gets you to a strain of about 1%. And if you're interested in elastic strains, that ain't good enough, because many of the systems we're dealing with have an elastic strain limit that's an order of magnitude lower than that. So by the time I've deformed anything to 1%, quite often it's already gone through a transition to the plastic region. And so if we want to understand the elastic strains, we need something with higher accuracy, higher precision to be able to map things. And so that's what really drove this interest in trying to get to the high resolution EBSD method. And I'll just quickly outline how the method works. It's in this paper which I wrote with Graham Meaden and David Dingley. Well, at the time this came out, 2006, the acronym somebody spotted, or the initial somebody spotted was WMD, which had all sorts of other connotations at the time. One of my colleagues has the quip, well, WMD, often cited, never read. To make some analogies to the other WMD. Anyway, basis of the method is we have our sample here, incident beam coming in, we get these diffraction patterns dispersed over a wider angular range, and if you follow what happens to some of the features on those patterns, if you then apply some loading to the crystal here so that you open up all the angles going vertically along that low direction, because we get a Poisson contraction, all the angles going horizontally get closed off a little bit, and that means that all these regions just move around, and they move around just a little bit. So the arrows I've got on there are very much schematic here. Things don't move anywhere near that much. Part of the problem actually is that more often than not, they move rather smaller shifts than a pixel, which means it's really hard to be able to see it by eye and really feel comfortable that it really is happening. So the reason it's called cross-correlation EBSD is the way we measure those shifts is through a cross-correlation process. And so just to talk through what cross-correlation is about, so I'm going to take two patterns, a sort of green one and a sort of red one. One's the test pattern here, so that's the thing I'm trying to match, and I'm trying to match it to some reference. And effectively what I'm going to do is shift one horizontally and vertically with respect to the other and see how well they match together. Okay? And then I'm just going to plot how well they match together as a function of the shift of the green and red ones over here. So you can imagine having some score in here that says how well do they match now, what if I move it over a bit, what if I move it over a bit more again and again, if I move it up. And you'll see how far I got before I got bored with that animation. And move to the cross-correlation function. So if we do that point by point, then what we find in here is that the high points in here, the bright points, okay, so the offset of that peak from our origin, from 0, 0, gives us the shift between those two patterns. Okay. Now it turns out that, although I've sort of described what happens in that cross-correlation in the direct space, it's computationally more efficient to go through a Fourier transform and do it in a frequency space. If you know about Fourier transform, it's fine, you'll understand what I meant. If you don't worry about it, go read the book. But it does mean that we go from, well, here's a region of interest, our diffraction pattern. We go into the Fourier space, and now distance out from the origin here gives us the frequency with which there is signal, and then the brightness of the spots in there tell me how much signal. There's a phase in there as well, which I haven't shown. But what you'll see is most of the information is in this central region in here. The rest of this stuff out here actually is just noise. So while we're in the Fourier domain, we may take advantage of that and actually we mask this stuff out, turn it to no signal there. And if I then back transform this back to the spatial domain, you see I've essentially got the same pattern, but I've taken out some of that high frequency noise on the top. If instead I want to compare two reasonably similar ones, I go through the Fourier domain, I take a conjugate, complex conjugate one, combine them, back transform, and that will give me this cross-correlation. We can find that peak to some pixel precision, and then we can do that over many regions on our pattern, and from that dispersion of chips across the screen, we can work out what's happened to the sample. Has it stretched? Has all the angles opened up this way, that way, which way? Has it all rotated round? That's just geometry. And so the simple experiment that we came up with, we're trying to measure this, is to take a really boring, perfect bit of silicon, put it in our microscope, and simply move the beam across the sample. If we move the point, the origin of our pattern spatially across, then the pattern itself has to follow with it. If we do that here through 11 points, all spaced 10 microns apart, then we can take 50 regions of interest dispersed across the screen, measure the shift from pairs of those points, which are all the same shift. So everything should give me the same number. Okay, it should be the same horizontal shift. And if I look here at a distribution here of those 500 shift measurements, you can see, well, there's a center to this distribution, which actually relates back to the pixel size, effective pixel size on our system. But more importantly, it's the scattering here, the spread in here, and you can see that this, hopefully you can read the scale in here, so this is going from 0.2 pixels here to 0.24 pixels here. So that spread in here is really very small indeed, far less than a pixel. You can make measurements, of course, with different beam conditions, more current, more signal, things like that. If you go from what I've shown there, about 400th of a pixel in that scatter, that was for a 1 second exposure, 1 by 1 binning, no binning on our camera, and this was taken on an old TSL Digiview 2 camera some time ago. If you integrate up, take some of the noise out, You can improve on that. Okay? We almost never do that. Okay? 1 second a pattern is far slow enough. So we tend not to do that. But if you convert that shift then of, let's say, 0 to 2 pixel shift, and you compare that to the camera length being several hundred pixels out from your screen to the sample, in this case it was 545, you divide this by that, you'll get the angle that subtends essentially, and that turns out to be, well, 4 10 to the minus 5 radians. So my strain sensitivity now is effectively down at this limit here. Okay? As I say, this is when we integrate out, we very rarely do that, so you lose some of this, it maybe gets a factor of 2 worse than that. A little bit of maths in here. This is really, don't worry about the detail in here, go read the paper, but essentially if you measure the shift, so here's our undeformed crystal, blue one, here's our deformed crystal here, green one, and if you take some zone axis, some feature, some direction in our undeformed crystal, it will move across and give you a shift here. The trouble is you can't measure this capital Q in here because part of that is kind of into the diffraction screen, into the detector screen, and you can't measure that. You only measure the shifts in the plane. So you're left with measuring this little Q here. And so it turns out, if you work through the geometry well enough, that you can set up, if you measure the shifts at one zone axis, you've got a vertical shift and a horizontal shift. That gives you 2 equations for the one zone axis. They look like this. You can separate it out. If you make the measurements at 4 features on the screen, that should be enough to get you to 8 degrees of freedom that are hidden in here that describe a rotation and the strain except for a hydrostatic strain. Okay. And the way we fix the hydrostatic strain is to say, well, we know we're making the measurements of the free surface, or very close to the free surface at least, probably just a little bit below that surface, but we're very close to that free surface, and we know something about the stresses of the free surface. A little bit of mechanics tells us that the stress perpendicular to that surface must go to 0, otherwise the surface would move. Okay? And so we take the direct stress across that surface and put that to 0, and that gives us an extra constraint, as long as we know the elastic constants that closes out the hydrostatic strain. And at that point you have all the components of your lattice rotation and lattice strain. How well does it work? Well, another simple experiment that we devised early on was, well, let's go back to our boring bit of silicon, and now let's use the SEM stage just to rotate it a little bit. Can we measure that rotation? And so this is a schematic saying, well, we start with some reference condition. I will apply small rotations that are on the limit, or possibly a little bit below the limit in terms of the specification of the stage in the SEM. In here, I'm going to take 5 patterns in each of these cases. We make shift measurements of 20 regions of interest in this case, and work out what that strain tensor, rotation tensor is. And this is the result in here. So here's our measured strain components here. Here's the nominally applied rotation. I'll say nominally just because it's actually below the specification of the stage, so whether it's genuine or not, I'm not entirely sure in here. But you can see we've picked out one component in here. It's a rotation around the X2 axis, which is what we were imposing on the sample through our rotation. All the other ones in here are staying down at 0, so that gives us some hope that there's a sensible measurement. But in some ways, more importantly, I was really more interested in how much scatter you get. So what I'm showing there, I think, is the means of those measurements, but we made repeat measurements of those, so you get some idea of the scatter, and that tells you about the precision of the technique. And this is then looking at the standard deviation of those repeat measurements of all the different components in our tensor, and you'll see that actually some we get rather better than others. So the ones down at the bottom here, so that in-plane shear, get quite a good fix on. Others out here, these red triangles out here is the 2-2, the strain sort of up and down the slope on the sample. But on the whole, this comes out about 10 to the minus 4, that sort of level. Okay. If you imagine somebody playing darts in a pub, you should think about the precision as to how the grouping of the darts on the board will end up. A tight clustering of the darts on the board is good precision, but of course they may or may not be tightly clustered in the right place. Okay? And the accuracy tells you whether that cluster is centered in the right place or not. Okay? So it's great to have good precision, but it would be nice to also know that we had decent accuracy. So one of the measures of accuracy in here, or one of the things that affects the accuracy, is how well we know the pattern center geometry and the screen to sample distance. If we don't know those right, then actually all the geometry that makes use of those shifts is going to be out. So here's an exploration of how that affects things. So the chart at the top in here, I'm looking at what happens as I change the pattern center position across the screen by, well, plus or minus 15% at the ends there. So that would be a horrendous calibration. It's the sort of thing that would make Joe or Mark DeGraff, who talked about calibration earlier on, it made them absolutely furious if you did that. You really do need to do better than that. But actually, the accuracy in our measurements is not so sensitive to that, as long as all the patterns are taken in the same geometry. If everything's taken in the same geometry, the absolute knowledge of that geometry is not so important. Okay? So as long as everything is a relative measurement in the same data set, you're fine. If you try and combine data sets or compare with simulations, then actually that goes out the window. In the standard method, the accuracy is good too. We also get some data quality metrics. We're going to make lots of measurements. We don't want to be worried about the individual points in here. We need some measure of how well we're doing all the way along. And so we have something that's akin to the mean angular deviation, or I forgot what it's called in the other bits of software, the mean angular error. So we make measurements of these shifts at lots of places. We end up with a best fit strain and rotation tensor, but then from those we can work out what the shift should have been in each of these regions and compare it to where things have measured things to have moved from. And these sort of size of these wedges, angular wedges in here, from the shift that we've measured and the shift we expect from our best fitting strain and rotation, gives us a mean angular error, okay, which gives us a measure of how precisely we're fixing that strain tensor. So we want our mean angular error to be small. The other thing we can use is actually to go back to the cross-correlation that we have at the start and measure the height of that peak in there. Because if we normalise things properly, so that our cross-correlation goes from, well, -1, where it's the same pattern but inverted contrast, all the way to +1, then actually the height of that peak tells us something about how good the match is. Okay? We make measurements at lots of regions of interest across the screen. We want it just as a single scalar in here, so we combine those by taking a geometric mean. So we multiply all those peak heights together and then take the nth root. Okay? We do it that way rather than arithmetic mean, because this way, if we've got a couple of row regions on the pattern where it's not working, it will take the geometric mean down quickly. So we are more likely to remove the row